Hello everyone, today we'll practice how to build a constant acceleration model. This problem says, freight trains can produce only relatively small accelerations and decelerations. A freight train moving at 4 meters per second accelerates at a rate of 0.05 meters per second squared for 8 minutes. It then slows down at a rate of 0.55 meters per second squared until coming to a complete stop. Build a complete model to describe the motion of the freight train. Okay, so I have included my kinematic equations because I know I need to describe the motion with equations and graphs, right? That's what we've been doing with kinematics. And we also said in class that for this class, will only have constant velocity. As you can see, we're given two different, not constant velocity, constant acceleration. As you can see, we're given two accelerations, which means we'll have two parts for this problem. When you have a multi-part problem, I think my suggestion is to start with the variables, because to build a complete model, we have to provide the 5 variables we agreed: velocities, time, and displacement. And then after you have your variables, it is, I think, easier to build your graphs. So let us start with part 1, which is concerned with this velocity, this acceleration, and then the time. So we'll label this one part 1. Okay. So we're given an initial velocity, right? That's the initial part of the motion. So we have initial velocity, 4 meters per second. Then we were given an acceleration of 0.05. That's it, right? 0.05? Yes. I am not going to be concerned with significant digits. I should, but I am not. Sorry. And then we're given a time of 8 minutes. We know that the unit for time, the SI unit for time, is seconds. So all we have to do is convert the 8 minutes to seconds. That's rather simple. All we do is multiply 8 minutes times 60 seconds, and we'll get 480 seconds. Okay, meaning we need to find the final velocity and displacement. So when you're going to select a kinematic equation, what you want to have is you need to have 3 known quantities. We have 3. And then you should be looking for a 4th one, okay? Even if the one you're looking for is not on the left side, let's say it's on the right side, it's okay. We can just do algebra and solve for it. For this one, let's start with initial velocity. So I want an equation, let's start with final velocity. I want an equation that has initial velocity, acceleration, time, and final velocity. And here it is, right? So I have initial velocity, acceleration, and time, and then I am looking for final velocity. That's the one I'll pick. Final velocity is equal to initial velocity plus AT. As you can see, we do not have to do any algebra whatsoever because the quantity I'm looking for, it's already on the left. So then I just plug in my numbers. Initial velocity is 4 meters per second. Don't forget the units. We have to get used to having our units. Acceleration is 0.05 meters per second squared. And the time is 480 seconds. Okay, let's use decimals. So that is 4 plus parentheses. Guys, your parentheses will be your best friends. Okay, make sure you use them. So there you go, 28. So then our velocity is, final velocity is 28 meters per second. Okay, so now let's find the displacement. For this one I have options. I can use this one, of course. I'm going to use the first one, uniform acceleration, just to show you a different way of rewriting this equation, okay? So this one says final position is equal to initial position plus initial velocity multiplied by t plus 1/2 a t squared. And as you can see, I don't need to find initial or final positions. I need to find displacement. So what I'll do is I'm going to subtract initial position, that is x naught, both sides. It cancels here. These two variables are not the same, meaning that I cannot combine them. So I would get x minus x naught. But we know that x minus x naught, final minus initial position, well, that is displacement. And then I can rewrite this equation in this form. I suggest you write it down somewhere in case you need to use it again. Then I don't have to solve for anything because my displacement is on the left side. I just plug in my numbers. So we have delta x is equal to initial velocity, that is 4 meters per second, multiplied by the time, that is 480 seconds, plus 1/2 acceleration, 0.05 meters per second squared, multiplied by the time squared. Okay, now let's go to decimals again. So we have 4 times 480 plus 1/2. Please note my use of parentheses, very important. And then squared. There you go. 7,680. We know that the unit for displacement is meters. So delta x is 7,680 meters. Okay. So we have our displacement. That's part 1. So for part 2, now we're going to be concerned with the slowing down at a rate of 0.55 meters per second squared until coming to a complete stop. This is your key. This is a very big clue. Implicit piece of information, okay? So let me change color for part 2. And for part 2, when the train began to slow down, well, my final velocity from part 1 becomes my initial from part 2 because it was at this velocity when the train began to slow down, right? So then my initial velocity is 28 meters per second. Because the train is going to come to a complete stop, my final velocity is going to be 0 meters per second. My acceleration, well, if it's decelerating, right, slowing down, then this number should be negative 0.55 meters per second squared. Now I need to find the time and displacement. If you can, it's always a great idea to find time, guys. Great idea. So let's see if we can have, if you have an equation with these 4. And here it is, right? We have final velocity, initial velocity, acceleration, then we're solving for time. For this one, we'll get to do some algebra, finally. So final velocity, initial velocity plus 8t. The first thing I'll do is I'll move initial velocity to the left, and I also know that my final velocity is 0, so I can, if I want to, I can just cancel it. So then these two will cancel, so on the left side I end up with negative initial velocity is equal to acceleration multiplied by time. Then to solve for time, I simply divide by acceleration. I'm going to flip my equation, okay? So time is going to be equal to negative initial velocity divided by acceleration. And I know this negative might look strange. However, our velocity is, our acceleration is negative. And that makes sense because we cannot have negative time, okay? There's no negative time. So then we'll plug in the numbers. So we have negative 28 meters per second divided by negative 0.55 meters per second squared. Let's go again. Let's use decimals. Negative 28 divided by negative 0.0. Oh, whoops. There you go. And then my time is positive as expected, 50.9. That's the time. So time is equal to 50.9 seconds. So now I have choices, I have options to solve for displacement. I'll just pick this one, right? Simple, short and sweet, the bonus one. That one says delta x is equal to initial velocity. Wait, let me write the equation. So initial velocity plus final velocity divided by 2 multiplied by time. I don't have to do any algebra. Displacement is on the left. Initial velocity is 28 meters per second. Final velocity is 0 meters per second. Divided by my time, divided by 2, and then multiplied by my time. 50.9 seconds. We'll just go to decimals. And I'm going to use the answer function, okay? This one's very helpful. So we have 28 divided by 2, brackets 28 plus 0 is 0, times, instead of typing 50.9, I'm going to select answer, and there you go. So my displacement is now 712 point, let's say 0.7. And that's meters. Okay? And there we go. We have all the variables or the quantities from part 1 and part 2.